Good day. So in this video, I'm going to go over the solutions um, to Codechef Starters 154. I'm going to go to solutions for A, B, C, D, E. Going to go in order of them, but I'm going to cover these 5 problems, which are from Division 2, and this is the only problem I'm not going to go over from Division 2, min-max paths, which also had not very many solves. Actually, this one from Division 1 had more solves, but that's interesting. But yeah, let's go over these problems from easiest to the hardest. So this first problem is add 1 or 2 game. So in this one, you're playing a game where you're playing a game with Alice and Bob, and basically you have an integer starts at 0, which is x, and essentially during a turn, Alice or Bob can choose to increment x by either 1 or 2. And so the goal is the game will end whenever x is greater than or equal to n. And if x is equal to n, then uh, Bob wins. Otherwise, Alice wins, which means that Alice wins whenever x is greater than n. So the goal here would be that Alice wants to make sure that x is greater than n, and Bob wants to make sure that x is equal to n. And the game starts with Alice going first. So first few things that I would do for this one, and I did during the contest, was just kind of writing out like base cases. So let's say, oh, hold on once. Oops. Okay. So let's say n is equal to 1. That was okay. So let's say n is equal to 1. That's like a base case. So for this one, who wins? Well, Alice wins. It's kind of trivial. Why does Alice win? Because, well, x starts at 0, and Alice will just choose to increment it by 2. And then it'll become 2, and then x will be, and 2 is greater than 1, so you're able to exceed it. If n is equal to 2, now what is Alice going to do? Alice cannot win, because if she increments it by 2, x is equal to 2 at that point, and basically Bob wins. If she does increment it by 1, well, then Bob is just going to increment by 1 and give himself the win. So, so there's no way she can win this, okay? What about n equals 3? If n equals 3, well, Alice could do 1, then Bob will do 2. If Alice does 2, Bob will do 1. Either case, Bob wins. If n is equal to 4, who wins? Well, Alice could do 1, Bob could do 1, Alice could do 1. Now Bob will win, right? Um, so if it starts out like this, where Alice does 1 and Bob does 1, then it's kind of obvious that Alice can't win, because now basically it's been reduced to the case of n equals 2 and Bob wins at n equals 2, right? If you do this, it's reduced to the n equals 2 case, where Alice starts, and Alice either does 1 or does 2. She loses if she does 2, and she'll also lose if she does 1, because Bob will do 1. Now, okay, that reduces that case. What if Alice did 2 initially? Well, then Bob has a choice to do 1, but why would Bob do 1? Because if Bob does 1, that reduces it back to the n equals 1 case. So you're kind of going from n equals 4 and you're able to bring it to n equals 1. But Bob's not going to do that. Bob will do 2 here, 2 here, which means that Bob will win. Um, so Bob will win in this case. What about if n is equal to 5? Well, if n is equal to 5, then Alice has an option to go and does 1. And then Bob can either do 1 or 2. either case, it reduces to one of these earlier problems then. This one, if Bob does, so if Bob does 1, after Alice does 1, it reduces to subtract 2, so reduces to n equals 3 case, which means Bob wins. If Bob does this, it goes to this state, and then Bob wins. Okay, what if Alice picked 2 initially? Then Bob might pick 1, or Bob will pick 2. And in this scenario, it reduces n equals 2, which means Bob wins. I guess I should write B for Bob. If this happens, it reduces to n equals 1, in which case Alice wins. But here's the thing. Bob is the one that makes this choice here. So he will, as long as he has an option that gives him back to a winning state, he will pick that. So he will always pick this one. And so Bob ends up winning again. And so you kind of see a pattern here where basically it looks like Bob will always win because you can always reduce it to one of these states, right? Like here, let's do this. Let me show it for a general. Um, so if n is equal to, let's say, 100. Now, let's say we've already solved up to um, up to 99, right? Like we kind of just kept doing a solution like this, or I guess 100 is really big. Let's just say n is equal to 6, right? So what do we know about 6? Well, there's what states can we go into from 6? Well, if Alice does 1 and Bob does 1, then you subtract 2, or you subtract 3, or you subtract 3, or you subtract 4. So that means it can only go subtract 2, or subtract 3, or subtract 4. And all of these states, so all of the 3 prior states, which just makes basically -2, -3, and -4, all of these previous like states, Bob wins in them all. So now you can see it all reduces to the previous. So it kind of has like a dynamic programming approach where if you've solved up to this value, then you know what the solution is up to like this current n. But yeah, you can also kind of see that actually Bob will always win from henceforth because if you go 3 back, it's always Bob winning here. So if you solve the base cases, then it extends like that. Now, I actually, during the contest, I didn't see this. So I actually wrote a mini-max algorithm, which is just a good, just like a good algorithm for these game theory problems. But essentially what it is doing is it is trying every possibility. So it returns true if if uh, if Alice wins, returns false if Alice loses. So it's basically returning true if the first player wins and false if they don't win. And the first player is Alice, so the turn whose turn it is or the player is 0 or it's 1. And then x is of course the value here of x. And and then yeah, you're gonna return starting from Alice's turn, starting from 0, and see what you can get. So if it's Alice's turn, and if there is a move that she can make that leads to her winning, which means it returns true, then she's gonna pick that. So you do or here, because if this one's leads to her winning, it will return true. She'll take this path. She'll increment by 1. If this one leads to her winning, it will increment by 2. Now for Bob, is slightly different. So for Bob, if it's Bob's turn, if he increments by, he wants it to be the case that one of these leads to Alice losing. So if one of these leads to Alice losing, then he will win. So if one of these is false, so that's why we use and here, because if this one's false, he'll make this move, and so this will return false, and so on. So, and this one's false, he'll make this move. But if this one's true and this one's true, then that means there is no move that he can make, and that's the only case right true. So I think another way to analyze this mini-max algorithm is using a Boolean tree or hold on. Yeah, I think there's another way to explain it if that's not clear. What did I just do? I don't know. It won't let me erase it either. It's weird. Oh wait, it's not even working right now. Okay. It isn't working right now for me. Oh boy. Okay, just do that. Okay, it's frozen or something. Okay, let's try this. I don't know what this is. I can't erase it though. Weird. Okay. It's not letting me draw some reason. Ugh. Okay, this is weird. Um, okay, I'm just gonna create a new one real quick. I don't know what happened to that one. Um, okay, I'm having some technical difficulties. It's not letting me draw anything. What the heck? This is weird. So this one, okay, now it's letting me draw. Okay. Try to fix this real quick. Okay, it's working now. I don't know what happened there. I just replugged it back in. So, anyways, okay, so the minimax algorithm you can visualize like this is that um, you have a function that kind of you can draw a tree to represent it as well. Like in each person's turn, there's two moves that they can make. So it's like a binary tree. Too tight here. Okay. So if it's Alice's turn here, Bob's turn here, Alice's turn here, Bob's turn here, and Alice's turn here. So in Alice's turn, it's gonna do kind of like a depth first search of this tree. So it's gonna kind of go down here. And so basically all we have to think about is if these two states, so if it's Bob's turn, we have this tree here, these options. Either he increments by 1 or he increments by 2. Now, if he increments by 1 and he goes down this path, it may return that Alice wins. And if he goes down this path, it may return that Alice wins. And this would be, um, and this will answer the question of does Alice win? And so in this case, Alice wins, right? If it's true and true, and it's Bob's turn, so this is Bob's turn or his node, it will turn true. But if this one's false and this one's true, or this one's false, oh no, sorry, or this one's true and this one's false, or this one's false. In all of these cases, Alice will lose in terms of Bob's perspective here, because Bob will make the appropriate act. Like Bob will choose the state that will lead to Alice losing. That is, if it's in this scenario, Bob will pick the x+1 path and traverse the tree, or the x+2 path, or this. But if it's Alice's turn, so let's say it's Alice's turn right here, um, then we want to know if Alice wins, and we either do x+1 or x+2 path, so it's binary. And for Alice, if this is true, this is true, this is false, this is true, this is true, this is false, this is false, this is false. She has the option here, so this will be she'll win. She'll win here too because she'll pick the winning path, and she'll win here. She'll only lose if both of them lead to false. So let's say, let's create an example of a traversal down like a path. Alice's turn, Bob's turn, Alice's turn, Bob's turn, Alice. So let's say this state leads to Alice winning, Alice winning. Let's say Alice wins here, Alice loses here. So in terms of Bob, Bob will lose, or Alice will win here. But in this case, Alice will not win because Bob can win, because Bob will pick the F path. So that is, if you're on this node, Bob will go here. If you're on this node, it doesn't matter where Bob goes because, anyways, he can't win. He can't make Alice lose. So in a sense, you're answering the question of Bob wants Alice to lose, and that in a result means he won. And then in this step, Alice will pick the path that leads to winning, so it's true here. So then this value is going to be true or false, really depending on what this is. If this is false, that is Alice couldn't win over here, then this will become false. If it's the other way around, if this is true, and that means Alice can win over on this side, then this will return true. And yeah, so it's essentially like that. Hopefully that makes some sense. But yeah, oh, I did that again. There are multiple approaches to this problem, and if you spend your time in it, it can be you can go a little bit in depth. Like you can use game theory. I think it's called an impartial problem. So this is my solution, but you could have just solved it with the observation that basically Alice only wins if n is equal to 1. Also, n is very small over here. But this is a binary tree, so this solution is, well, this solution is actually 2 to the n. So the only reason so this is more of actually a brute force solution now that I think about it, because 2 to the n operations, because a binary tree, so each node has 2 child nodes. So in total, it'll be 2 to the n, so 2 to the 10 operations. But if you use the observation of the dynamic program or something, you can solve this in linear time. Or you can solve this in constant time if you just make the observation that Alice only wins if n is equal to 1. So yeah, a lot of solutions. Let's actually just implement that one real quick. So let's just say if to 1, and then, yeah, so this is what I mean. This is the constant O of 1 solution. But yeah, obviously they're allowing you to use a minimax. You don't have to make the observation. Okay. So for this one, GCD and XOR. So you read this one, it seems a little bit difficult, but this is the core of the logic actually right here. It looks difficult over here, but it's not as hard as it seems. Like it just tells you have an array of size n. You can choose an interval from L to R and then some x value, and then you can do either of these things with this interval or range. You can XOR every element in the range, or you can do the GCD with every element in the range with the x value. So you want to choose your subarray A and your x, and either replace every element of the subarray with a GCD with x, or replace every element. Yeah, okay, let's explain that. Compute the minimum number of operations required to make all elements of the array equal to k. So how do you, yeah, so what's the minimum operations to make everything equal to k? Well, um, I think the best thing to do here is just to think about like some observations. Like, for instance, when would it take 0 operations? Like, ask that question. When every element, or let's actually just write this out. So let's say, when would it take 0 operations? When, if every element in the array is equal to k, right? If everything's equal to k, you don't have to do anything. Um, okay, when would it take 1 operation? Um, so yeah, when would it take 1 operation? It would take 1 operation if, I would say 2 scenarios. There's two, if 1 operation means either you're going to do the GCD or you're going to do the XOR. So let's say we're doing the XOR. So if we're doing the XOR, it could take one operation if you have a continuous, yeah, you have a subarray where all elements are not equal to k, but they are all equal, right? So let me draw this out. This one's a little bit harder to see. Why is this? Oh no, did it freeze? Oh, it's weird. It looked like it froze, but it unfroze when I did that. So this one, the XOR is kind of complicated. So let's say you have some values that are equal to k already, and then you have a value that's like v and v and v and v, and then k, k, k. So all you have to do is take this and XOR it with an x such that it's equal to k. So in fact, you know what x needs to be. X needs to be equal to v XOR k. If you just take this as your x value and you XOR every element in this subarray, you will get everything to be equal to k, and that's one operation. That's required. Now it won't work. Now that it's important that all elements in here are equal, because if you have v and then u and then v, if you have like different values, it's not going to work. You can't XOR this and get k, because u XOR x and v XOR x are always going to equal something different. Yeah, like those just aren't equal. So that would not work. But it's not just enough that it's not just enough that all the elements are equal if they're not equal to k. It's also very important that it's one subarray. Like this, you can't do this in one operation because you can't take this whole subarray and convert it to k because you have these k's here. And obviously kx or k will equal 0 and mess those up. And I think k is never equal to 0. Yeah, k is never equal to 0. Um, so what you can do is you have to XOR this and then XOR this. So okay, it's more than one operation. So the only way it'll be one operation if you have one continuous subarray. What about GCD? When would it be one GCD operation? Well, one GCD operation would be basically if you take the GCD of every element in your array, every element with some value x, it's equal to k. Well, not some of the element x, it will actually be k itself because um, because that's how you can get k is if the GCD is this. Like, okay, well, the GCD of k and k will equal k. So if it's already equal to k, it will already work. If it's not equal to k, but it's like, I don't know, some multiple of k, then you'll get k from it. So it will do it in one operation, potentially. But so those are your two options of one operation. What about two operations? So for two operations, um, when would it take two operations? Let's think about it. Um, so here's kind of a trick that I kind of observed. Given an array of elements, some elements are equal to k, some are not equal to k. So whatever. Just do this. Take the GCD of everything with one of the entire array. So I is an element of 1 to n or 1 to n. So just do it for every element, and that will convert every element to 1. So then you'll just have a bunch of 1s. Then if you want to get k, all you have to do is do 1 XOR with k, so set x to k, and then you'll get k. And in that case, it'll take two operations. What this means is that at most, it'll take two operations. So it will never take more than that. So I don't know why it keeps freezing like this. I have to keep unplugging this. So all you have to do is check if it's going to be 0, 1, or 2, and it's very easy to check. So 0 if all the elements are equal to k. You can use alla underscore of in C++ to do that, and then you just pass in the beginning iterator, the end of the iterator, and then pass in an anonymous function. Where I guess technically this it didn't need to what's the word? it didn't need to get all the variables from this scope. I think that's I forget what they call this, but I know what this is doing. This takes if you put and in here, it means that I can access the array in here. If I don't do that, I can't access the array in this anonymous function. But this should work because I don't need to access the array in here. I can also access the array by just doing like this specifically, but if I do this, it'll access every variable. So I guess technically you could say it'll access nk. Oh, I do need this because I need to access the k in here. Okay. Of course I could just do specify the k, but might as well just have it be able to access everything. So anyways, yeah, so it's the anonymous function. So see out 0. And then C out 2 will be what it'll do if it can't do it in one operation. So when can you do it in one operation? Well, one of them was if you can take the GCD and it's equal to K. The other one is, well, I write this function called check. You probably come with a better name, but essentially what the function will do is it will check that you have that continuous segment where all the values are equal when they're not equal to K. So yeah, I just track the values in indices. So I just find where they're not equal to k, do that, and then I just confirm that all the values are first off equal, and then I confirm that they're all continuous, that is consecutive in terms of the index. They're adjacent to each other in the array. And if they're not, then you return false. Otherwise, you return true. So okay, so that's the solution for that one. Hopefully that makes sense. This problem. Okay, I'm trying to remember what order these were in the contest. So I think this is the one that was the next in terms of difficulty, which I can tell based on the number of submissions. So yeah, so this one should be next in difficulty. So triangle count easy. So this one is just asking that um, you're given an array of distinct elements, and what you want to do um, is count the number of values that I can pick, the number of basically given my array of elements, I can pick 2 elements from the array. So here they say BI, BJ. And then I pick X, but I choose what X is. So I choose what X is, it can be whatever. But the point, the crucial thing is that whatever I pick for X, these represent lengths of the side lengths of a triangle. So they need to be an actual triangle. They need to be a non-degenerate triangle. And and so non-degenerate triangle just means like a triangle with positive area, like a real triangle, not like so you can have like collinear stuff, but yeah. So I mean, it says right here, non-degenerate triangle is one with positive area. So yeah, you want to find the number of distinct integers you can pick for x. So how do you solve this one? Um, okay, so um, the go here. Oh, so for this one, you can solve it by um, by kind of thinking about it. So kind of I wrote out stuff and was kind of looking at it. The first thing you need to know though to be able to solve it is the triangle inequality. This is, I would say, a prerequisite, or at least I use this to solve it. So basically what this says is given a triangle of A, B, and sides C, is that it just says that A plus B has to be greater than C, A plus C has to be greater than B, and B plus C has to be greater than A. So the first thing I did with this observation was like, let's say I'm picking A, B, and C. So C is like my X. So let's say it's X. So say I have 2 values A, B. So what this inequality is saying is that A plus B has to be greater than X, A plus X has to be greater than B, and B plus X has to be greater than A. Well, let's suppose that in this scenario, B is greater than A, and they're distinct, so you don't need to include equivalent. So I think I scrolled down too far. Okay, so basically, what you can say is that I see. So basically, what you say is, well, you think about how this kind of constrains X. Like this right here is saying that X has to be less than this, right? Like if you just rearrange these, like these two here, you're saying that X has to be greater than B minus A, and you're saying X has to be greater than A minus B. But since B is greater than A, uh, um, uh, this one will just be saying X has to be greater than a negative. So this one will be greater. That is, B minus A is greater than A minus B, right? Because A minus B will actually be negative, in fact, and this will be positive. So this is what you're actually going to use to constrain it. So you can ignore this one. So that means you just need to look at these two conditions, which says that if you rewrite it, which says that X is between these two. So any X that is between these two ranges is valid. So now you have a way to kind of do it. You could maybe solve this in O of n, n squared, where you just go through every possible pair of side lengths, so every possible A and B value, but always where B is greater than A, and then you can find your range of X values, and then you can iterate over the range and like add them into some set or something. So that way you'll get all the count of the distinct X values that are valid. You can also rewrite this. I think I did this to make it easier. I thought it made it easier to work with, which is if you add one to this side, then you can do greater than or equal. And if you subtract one from this side, you can do that. And in that way, you're constraining it with this exclusive range. I think I did this to solve it. It made it easier. But anyway, so yeah, so you can solve it O of n squared, sure. But that's not going to be fast enough. So you need to come up with something faster. So really, what you can do is kind of look at some relationships. Really, um, like what happens if, let's say you have a value here. Let's say it's 5. And let's say you have some previous values of 2 and 4, right? And I just want to note something here. If I use this 5 with the 4 and I use it with the 2, where basically I'm saying like my 5, 4, and then 5, 2, and then x, and I solve for x in these terms, this first one will tell me that x is between, again, it's going to be 5 minus 4, so it's going to be 1. So it's going to be 1 if I go back to this, or if I'm doing it, if I add 1 to it, then we'll do the greater equal to, and then 9 minus 1 is 8. But this other range will say that x is between this, which is 5 minus 2 is 4, and then x is less than or equal to 5 plus 2, which is 7, 1 minus 6. And so anyways, what I noticed here was that when I'm taking an integer here and I'm taking values that are smaller than it, that that I only need to look at the value which is nearest to it, because everything else, this right here is actually nested in this range. That is, you have a range on a number line that is 2 to 8. This other range is just 4 to 6. So it's literally just a subinterval in here. And that's the thing, is it's nested within the other range. So as you go further back, it's going to become nested. And you can think of it further why that's the case, because when you take the 5 and you take the nearest element, when you do the subtraction, you're going to get the smallest possible value. It's going to always be getting larger if you go further and further back because the distance is increasing. And when you're taking that difference between the 5 and that number, that's going to be increasing. Yeah, so it will be greater than 2. But at the same time, the sum of this and that element is going to be smaller. So you have this thing where the lower bound is going to be greater and the upper bound is going to be smaller. So you can kind of argue that it's always going to be nested. And so you really only have to take the adjacent element. And I argue that all you have to do is sort your elements. So I think they give an example that was really useful to work with. I think this is the example I worked with. Um, let's see. So if you take this example, you can sort this. That'd be the first step. So you do 1, 3, 5, 6, 17, 50. And then all you're gonna have to do is then create your AB here, and then create your AB here, and then create your AB here, and your AB here, and your AB here. So okay, so that's linear time complexity. But these are gonna create like different ranges. So I think you end up getting a range here from 2 to 3, and you end up getting a range here from 5 to 3, 3 to 7, and then here from 5 to 6 you get a range of like 2 to 10, and from here to here I think you get a range of 12 to 22, and then here I think you get a range of 34 to 66. And so um, if you sum these intervals up, by the way, so first off, this one is actually intersecting with this one, um, which is interesting. Um, oh, sorry, this is actually 3. This is 3 here, because 3 minus 1 is 2, plus 1 is 3. So this is 3. Okay, I can't even read that now. Okay, yeah, so this one's 3. So what I actually did for my solution is I thought, well, these ones that are nested, I don't care about them. So what I did was I sorted these intervals, and then by sorting it, it allows me to handle the intersection because that means um, and basically you want to count the total range of x values. But what that means is I'm going to get something with a 2 and then it ends at a 10, right? And then next I'm going to get something which starts later. So maybe it starts at 3 and goes to 3, whatever. Or maybe it starts at 4 and goes to 7. Or maybe it starts at 5 and goes to 15. Okay, maybe it exceeds. Well, all I need to know, since I sorted based on this character first, is that I calculate my first range, which is 9 or something. So I add 9 to my answer or so. And then I set this as my upper bound. So when I process this range, I notice it's completely, well, I know the start will happen after this start, and I see that the end doesn't exceed the upper bound, so I know it doesn't add anything. And I know this one doesn't add anything. This one though, it will add something because it's 15. You take the 15 minus 10, you get something like, okay, it adds like something like that. And that's kind of what I did. So I guess I'll show the code here. So basically I sort the array, I get the answer, I'm going to form my intervals, and then in here I should form the left and the right bound, basically using the thing that I showed. So this is guaranteed b is this and a is this, and then add 1 and then so on, and then add this interval into here. Then I sort the intervals. I set upper originally to negative infinity, and then the value that this will contribute, this interval that is, be either 0 or it'll be the right interval minus the max of upper and wherever the current left point is. So for the 210, it would end up taking the 2, and so it would end up taking 10 minus 2 plus 1, so an increment by 9. And then I just have to make sure I update the answer, and I update the upper by taking the max of what the upper is, and then r plus 1. I just add plus 1 because technically I took the 10, so it needs to be looking for 11 from here on. So then if it gets to the 15, it would go from 15 minus 11 and it'll grab 5. Yeah, so this actually worked. So that's that problem. Hopefully it makes sense. For this one, okay, so this one I actually didn't solve during a contest because I thought it was harder than this one. But I learned it after the contest. I guess it is pretty easy. Let me check my battery. Okay, so tree cut XOR. You're given a tree with n, what are we looking at here? Okay, so you're given a tree with n vertices. Initialize variable x equals 0. You'd like to perform the following operation n minus 1 times. So you're going to choose an edge that still hasn't been deleted, delete the edge, and then what you do is the nodes, the edge that you deleted, it has two nodes. Those two nodes are part of their own connected component now. And basically what you're doing is you take x and you XOR it with the size of one of the components, either the size of the component that u is a part of or the size of the component v is a part of. And then you want to calculate the minimum possible value of x that can be achieved after performing like n minus 1 operations. That's how many edges there will be. And you also, this makes it a little more challenging, you want to provide a valid sequence of operations that achieves this minimum value of x. And it doesn't care what you provide there. So the way to solve this is to kind of just look at base cases and work up from there. I think the smallest tree is 2. So you don't really care about the structure of the tree. That's one thing you can kind of abstract away. So n is equal to 2. Can n equals 2, what can x be equal to? X will have to be equal to 1 here. Why? Because there's one edge, and when you do the delete, you're going to have to XOR 0 with 1. Okay. If n is equal to 3, that means you have an even number of edges. If you have an even number of edges, then all you have to do is take that 0 and XOR with 1, XOR with 1. So basically, the strategy for this is if you have 3, is 3 edges, is delete here, and then the size of this one. So basically, given the tree, delete an edge where, or take a leaf node and disconnect the leaf node from the tree. So a leaf node base is where the degree would be equal to 1. So take a node where the degree is equal to 1 and delete it. And then update the degrees of this one, because then you're going to be able to take that node and delete it. And when you do that, the size of the connected component is always 1 for that node. And if you take 1 and you XOR 1 in, an even number of times, it will always equal 0 because it'll always cancel. So in that sense, there's a very easy, so it's easy to find the operations. You're just always going to delete the node with a degree equal to 1. And you can do this with like a depth first search, where you track the edges in like a stack. And that way you can backtrack through the stack, and that way it'll delete the edges that are like at the bottommost, and and it'll make sure that it'll delete the edges like I don't I don't know if it's clear, but like you just have to make sure that in this case it'll put this in a stack. So this is B C D E, A B C D E F. These are the edges. It might put A into the stack, then it'll put B, then it'll put C, then it'll put D, then it'll put E, then it'll put F. So obviously if you delete F, you're good. You delete E, you're good. Now it'll delete D, but it will have already deleted everything under D. So you're good. This node is currently a leaf node. And then it'll do the same thing on this side. B, a C, B, and an A. So yeah, so if n is equal to 3, it's that case, and it's very easy to generalize it. I don't know if it's generalized, but extrapolate it to basically when n is odd, you'll have an even number of edges, and so just always delete the edge where you have a component equal to 1. So if n is odd, you know the answer will be x will equal 0, and you also kind of have a strategy to build those operations. So if it's even, the very first example of an even length one was 1. So you really need to ask a question of what happens when you go bigger with even. Is it possible that x could be equal to, if it's even length, it's obvious that it's going to be equal to 1 because, boom, I have an odd number of edges, and if I just take 1 each time, I will basically get 1. So it's obvious you can do 1, but can you do better? Well, if you take n equals 4, so it's kind of easy to work with these small examples, um, you can say that you can delete, um, it's hard to see it, but maybe, I don't know, maybe it's easy to see. So you have this. If you delete this, you take the 1 and you delete this and you take the 1 and you delete this, take the 1. Okay, well, that's just going to give you 1 again. But can you do better? Well, if you delete this, you can take the 3, you can take this side instead. And then when you delete this, you can take the 2. And then when you delete this, you can take the 1. That gives you 0. So there is a way to get x equals 0. So actually, the only time you'll get x equals 1 is when n is equal to 2. And for this, you will get this. And then you can solve this problem really easily by basically, like, you don't care what happens in for the edges. Like, you just have to make sure that for the 3 last edges in your stack, that you remove them in this order where you pick the node of the larger component. And that's all you have to do. You can basically, for when n is even, you can remove the leaf nodes until you get to the point where there's only 3 edges remaining. And then you do this strategy, and it'll guarantee you'll get 0. Um, Additionally, it guarantees you get 0 because that means you would have processed an even number of edge lengths before. So the ones would have been XORed an even number of times. And so this last 3 you'll treat in this special manner. I feel like that makes this problem a little hard. Like, I feel like it's very greedy and you have to make that observation. And you kind of have to know how to work with trees and everything. So yeah, so build the tree with adjacency lists, very common representation. Perform the depth first search, which really builds up those edges in a stack. And then I say the answer is either 0 or 1, right? And then it goes through the stack of edges, and essentially if it's odd or if there's more than 3 edges, you're going to pick U and V, and you're going to pick V as the leaf node, so you're going to pick that one because that's equal to the size of that will be 1. But if it's even or the edge size is less than or equal to 3, then you're actually going to pick the larger side. And so this works for that one. Okay, I need to check my battery. Okay, I might be able to finish. Because this one I don't think is actually that. This one's supposed to be the hardest one, I believe, out of those 5. Oh no, actually I think I maybe did this and no, this was supposed to be the hardest one. Okay, so I did this slightly out of order. Regardless, it's okay. So this one's supposed to be slightly easier than tree cut XOR. Um, so in this one, basically the problem is, um, you basically are given an array of zeros and ones. You're given a binary array. And for each subarray, you want to do this. So for each subarray, you read this part and it tells you if that subarray can be winning. And it can be winning if for that subarray, you can get every element in it to be equal to 1 by using this operation here. And this operation here is that you can take a range in your subarray, right? So it's kind of like you're taking a subarray of a subarray, but and you can ignore that, but that is kind of what I thought. But you're taking a range in that subarray, and you pick a range such that the number of ones in that is strictly greater than the number of zeros in it. And if that's the case, you can change everything to 1. So there's a very specific rule for when you can change everything to 1. Um, so, um, so basically, um, what you can kind of observe, I think, really quickly um, is that if you have something like 1 1, right? Let's say you have a bunch of zeros here, blah blah, whatever. These don't do anything, right? And then you have a bunch of zeros here, okay? Like, it looks like, and let's say you're trying to form a subarray here. Okay, that subarray is not going to work, right? There's no way to get it to be all ones. This subarray is not going to work. This subarray is not going to work. There's no way to get it to be all ones because if you pick this part, the count of 1 and zeros are equal. Okay, it doesn't work. Let's say you pick this subarray. This subarray works because with these 2 ones, you can change everything in here because you can pick this subarray and change all these to ones, and then pick this one and change all of them to ones, and then pick this one all of them. So you kind of like you can keep performing the operation to get everything to be equal to 1 in here. So this subarray will actually work. So this is a very important thing because as soon as you see a 1 1, it will work. So if you consider this subarray, it will work. If you consider this one, it will work. So you actually just need to track where at least two adjacent ones exist in your array and track the last time you've seen it. So kind of iterate over the array from left to right and then track the last index um, where you see two adjacent ones, because basically every subarray from there you can take all of these, right? All of these you can take. So whatever the length is from here to here, you can take all of the subarrays. So I can take, so I'm at a point over here, and then I find my last one is right here, and at the beginning of the array is over here. So whatever the length of this is, I can take that many subarrays, which I can make them all equal to one. Um, but there's one other case that you have to be aware of, which is this one, 101. So a zero sandwich between two ones. You can use this to convert everything to ones as well. So it's basically this very similar, because you can take this range and now you have two ones and one zero. So you have strictly greater. So you can convert all that to ones. And now you just can keep using that and cascading it to convert everything to one. And so you can do that. And then and yeah, and basically that will work. And basically it's the same thing as the one above. So if you have a 1 1 and then you have a 1 0 1 and then you have wherever you're at right now, you want to take the earliest, because whichever one appears first, if the 1 0 1 appears not first, but the one that appears last, most recently, in terms of that you're iterating from left to right, you want to pick everything from here, because everything from there you can convert to one now, each subarray. Um, so basically, this is my solution. Sorry, I'm going fast on this one because I think this is taking me a while. So maybe I'm not covering this one in as much depth as some of the other problems, but I mean, hopefully it helps out and it's a little bit clear. But yeah, you can just set last one, last two. I think last one I picked to be the adjacent ones. I didn't say it here, but so this is my adjacent ones, and so it goes through the array, and yeah, so it checks if you have two adjacent ones, and it tracks the last time you saw it. And then it does -1 because it technically starts here. And then this is looking for the sandwich 1 and 0. So it looks for this one equal 1, this one equals 0, this one equals 1, and then sets it back 2 because 1 0 1 starts 2 before from wherever you're currently at. And then you take the difference and you say the max of last one, last two. So you take the one that's nearer to your current index and you add one to it. Yeah, that's just like a thing you can figure out pretty easily, and then you increment that difference in the answer. And then the only thing I didn't count in here was I didn't count the ones themselves. So each one individually also contributes as a subarray, where it is a winning subarray, that is. It just consists of ones. So just add all the ones back into it, and then that should be the answer. Okay, so that's it. So hopefully that's clear. But that's all I'm gonna be able to cover for now, I think. Um, all right, so until next time.